Imagine a lie so paradoxical that it defies logic itself, one that cannot be true or false without contradicting itself. This is the Pinocchio Paradox, a self-referential statement that challenges our understanding of truth and falsehood. The paradox arises when Pinocchio, the wooden puppet whose nose grows whenever he tells a lie, utters the sentence, "My nose will grow now." The contradiction becomes immediate. If the statement is true, then his nose should grow. But his nose only grows when he tells a lie. This means that the statement must be false. But if the statement is false, then his nose should not grow. However, that would mean that he is lying, which should cause his nose to grow after all. This infinite loop of logical contradiction places the Pinocchio paradox among the ranks of famous self-referential paradoxes, like the liar paradox, where a person states, "This statement is false." If the statement is true, then it must be false. But if it is false, then it must be true. The Pinocchio paradox is unique, however, because it involves an external, physical consequence, his nose growing, which directly impacts the truth of the statement in real time. This paradox raises fundamental questions about logic and self-reference. Can truth exist in a system where statements can alter reality? If Pinocchio's statement is both true and false simultaneously, does that mean our binary understanding of truth is flawed? Could there be statements that exist outside of traditional logic, neither fully true nor fully false? Beyond fairy tales, the Pinocchio paradox has deeper implications. Self-referential paradoxes appear in philosophy, linguistics, and even computer science. For example, in programming, certain conditions can create infinite loops, where a program gets stuck repeatedly checking a rule that contradicts itself. In artificial intelligence, self-referential logic can create conflicts in decision-making models. In real life, we see echoes of the Pinocchio paradox in legal loopholes and paradoxical rules. Consider a law that states, "This law must not be followed. If you follow it, you break it. If you break it, you follow it." Such paradoxes reveal the limits of rigid logical systems and force us to reconsider how we define truth in different contexts. Some philosophers argue that the Pinocchio paradox exposes a flaw in our reasoning rather than in reality itself. Perhaps the problem lies in our insistence on absolute truth values, rather than accepting that some statements exist in a gray area, neither fully true nor fully false. Quantum mechanics, for instance, introduces the concept of superposition, where a particle can exist in multiple states at once until observed. Could truth itself work in a similar way? Ultimately, the Pinocchio paradox serves as more than just an amusing riddle. It forces us to confront the very nature of language, logic, and truth. If a single sentence from a wooden puppet can unravel our understanding of reality, what else might be waiting to challenge the way we see the world? Imagine walking into a room full of strangers and being told that at least two of you share the same birthday. Your instinct might be to doubt it. After all, there are 365 days in a year, and surely birthdays are spread out enough to make that unlikely. But mathematically, this situation is far more probable than it seems. This is the birthday paradox, a counterintuitive probability phenomenon that challenges our natural understanding of chance and coincidence. At its core, the birthday paradox demonstrates that in a group of just 23 people, the probability of at least two individuals sharing the same birthday is an astonishing 50%. Increase the group to 57 people, and the probability jumps to 99%. This seems absurd at first. How can the odds be so high with such a relatively small group? The key lies in how we think about probability. Most people mistakenly frame the problem in terms of their own birthday matching someone else's. However, the paradox doesn't focus on any one specific birthday. It considers all possible pairs within the group. In a room of 23 people, there are 253 unique pairs of birthdays, each with a chance to match. With so many comparisons happening at once, the likelihood of at least one match becomes surprisingly high. To put it another way, imagine flipping a coin. The chance of getting heads twice in a row is just 25%. But if you flip it 253 times, the probability of getting at least one double heads outcome is overwhelmingly high. The birthday paradox follows a similar principle. As the number of interactions grows, so does the chance of a match. Beyond a mathematical curiosity, the birthday paradox has real-world applications. Cryptography, for instance, relies on the difficulty of finding specific matches in vast data sets. But the paradox reveals that collisions, unexpected matches, are far more likely than intuition suggests. This principle is used in designing secure hash functions, ensuring passwords and encryption keys remain difficult to predict. The paradox also applies in genetics, where it helps scientists understand the probability of shared DNA markers among populations. In epidemiology, it assists in modeling how diseases spread within groups. Even in online security, where digital fingerprints and file checksums must remain unique, the birthday paradox warns us that accidental duplicates occur more frequently than expected. But beyond its practical uses, the birthday paradox forces us to confront how flawed our intuition about probability truly is. We often underestimate the power of exponential growth and interconnectedness. Just as in the paradox, where a small number of people leads to a surprisingly high probability of a shared birthday, many real-world systems behave in non-linear ways, where small changes lead to massive effects. And then comes the deeper, more philosophical question. If coincidences like shared birthdays are far more common than we think, how many of our so-called rare experiences are actually inevitable? When you meet someone with an eerily similar past, or stumble upon a book that answers exactly the question you've been wondering about, is it truly fate, or just another instance of hidden probability at work? Ultimately, the birthday paradox is more than just a fun statistical quirk. It's a reminder that the world is far less random than it appears, and that patterns, coincidences, and improbable events might not be so improbable after all. Imagine you are given 2 envelopes, each containing some amount of money. You are told that one envelope has twice as much as the other. You randomly pick one, open it, and see, for example, $100 inside. Then comes the question, should you switch envelopes or keep the one you have? Welcome to the 2 envelopes paradox, a deceptively simple yet deeply perplexing problem that challenges our understanding of probability and decision-making. At first glance, switching seems like a 50-50 choice. After all, there are only 2 envelopes. But let's apply some reasoning. If your envelope contains $100, the other envelope must contain either $50 or $200. Now, if you switch, you have a 50% chance of doubling your money and a 50% chance of halving it. The expected value calculation seems to favor switching, If the other envelope contains $50, you lose $50. If the other envelope contains $200, you gain $100. Since these probabilities appear equal, the expected value of switching seems to be 0.5 times $100, $50, plus 0.5 times $200 equals $125, which is more than the $100 you started with. This suggests that you should always switch. But if that were true, then switching again would also seem beneficial, leading to an infinite loop of irrational decision-making. Where did the logic go wrong? One of the core problems is how we assign probabilities to the amounts inside the envelopes. The paradox assumes that the probability of the other envelope containing half or double the money is always 50%. But that's not necessarily true. The distribution of possible values plays a crucial role. If we do not know how the amounts were chosen in the first place, then treating them as symmetrical, one being always half or double the other, is misleading. This assumption creates an illusion of an advantage where there isn't one. Mathematicians have proposed several resolutions. One approach is to consider the prior probability distribution, how the amounts in the envelopes were initially determined. If there's a fixed maximum amount that could be placed in an envelope, then switching does not always yield a consistent advantage. Another perspective suggests that because the problem is framed in an ambiguous way, it creates an illusion of expected value gain that doesn't exist in a properly formulated probability space. But beyond the mathematics, the two envelopes paradox reflects a much deeper philosophical and psychological dilemma. How do we make rational decisions when faced with uncertainty? This paradox forces us to question our own instincts about risk and reward. Much like the famous Monty Hall problem, where intuition misleads us into making the wrong choice, the two envelopes paradox exposes flaws in our understanding of probability and expected outcomes. The implications stretch into economics and game theory. Imagine an investor deciding between two stocks. One might double in value while the other might lose half its worth. The reasoning behind the two envelopes paradox mirrors the kind of irrational financial decisions people make when they misinterpret risk. It highlights why investors sometimes jump between assets unnecessarily, thinking they're maximizing returns when they may just be caught in an endless loop of indecision. More broadly, the paradox ties into decision theory and uncertainty in real life. If we cannot definitively assign probabilities to our choices, should we still switch? Should we second-guess every decision, or sometimes accept the uncertainty? And if switching always seems beneficial, is it possible that our framing of the problem itself is flawed? Ultimately, the two envelopes paradox serves as a humbling reminder of the limits of intuition. It exposes the ways in which logical reasoning, when misapplied, can lead to paradoxes that defy common sense. While it might not offer a simple answer, it leaves us with a crucial question. When faced with uncertainty, should we always try to switch to something seemingly better? Or is the real paradox that we might just be overthinking it all? Imagine a donkey standing precisely between two identical piles of hay. Both are the same distance away, both equally fresh, and both equally appealing. The donkey, unable to decide which pile to eat from, starves to death, not because of a lack of food, but because of an inability to make a rational choice. This is Buridan's ass, a philosophical paradox that exposes the limits of logic, decision-making, and free will. At its core, the paradox raises a fundamental question. What happens when a perfectly rational being is confronted with two absolutely equal choices? If there is no difference between the two options, then how can any rational criteria be used to choose one over the other? Buridan's ass suggests that in such cases, the individual would be trapped in perpetual indecision, leading to inaction. The paradox originates from the work of the 14th century philosopher Jean Buridan, though ironically, he never actually proposed this exact scenario. Instead, Buridan explored the idea of determinism and free will, questioning whether humans, or rational agents, truly have the ability to act freely, or whether their actions are governed by external causality. The image of the starving donkey was later attributed to him as a way of illustrating the absurd consequences of strict rationality. At first glance, this paradox might seem like a simple thought experiment, but it has profound implications for philosophy, economics, and even artificial intelligence. If a rational being cannot act without a decisive factor pushing it one way or another, does this mean that pure rationality is insufficient for survival? Does true decision-making require randomness, emotion, or some external force to break the tie? Modern interpretations of the paradox extend beyond just a donkey and two hay piles. Imagine standing in a supermarket aisle faced with two nearly identical brands of cereal. If they have the same price, the same ingredients, and you have no prior preference, which do you choose? Or consider an online shopper staring at two identical products with identical reviews. Does their choice come down to a subconscious impulse rather than logic? This highlights an important insight. In many real-world cases, our decisions are not always based on pure rationality, but on biases, instinct, or external nudges. This paradox also has direct applications in artificial intelligence and decision theory. If an AI system is programmed to act purely rationally, how does it handle situations where two choices are perfectly balanced? Without some form of tie-breaking mechanism, an AI could theoretically become trapped in infinite indecision, unable to act. This is why modern AI incorporates elements of randomization or secondary preferences to ensure it can still function when faced with seemingly equal choices. The paradox even applies in the realm of economics and game theory. Businesses often face two competing strategies that seem equally viable. Governments struggle to allocate resources between two equally urgent needs. Investors hesitate between two equally risky stocks. In each case, pure logic alone may not be enough to make a choice, and external factors, like intuition, chance, or even arbitrary deadlines, often push the decision forward. One of the most fascinating aspects of Buridan's ass is how it ties into free will and determinism. If we believe that every action we take must have a cause, then when faced with two perfect options, shouldn't we be unable to choose at all? But in reality, we do make choices, often arbitrarily, based on gut feeling, social influence, or even sheer randomness. Does this mean that human decision-making is less rational than we assume? Or does it suggest that true free will might involve an element of unpredictability? So how do we escape the fate of the donkey? One possible solution is acknowledging that no two choices are ever truly identical. Even in cases where options appear equal, there are almost always subtle differences. A fraction of a second's hesitation, an unconscious bias, a minuscule variation in experience. Another solution is to introduce randomness. In the real world, we often make arbitrary decisions simply because we have to keep moving forward. We flip a coin, follow a whim, or allow outside circumstances to tip the scales. Ultimately, Buridan's ass is more than just a paradox. It's a mirror reflecting the complexities of human decision-making. It forces us to confront an uncomfortable truth. Perhaps pure rationality isn't the ultimate tool for survival. Perhaps in order to truly function, we need intuition, randomness, or even irrationality to help us break the ties of endless deliberation. And maybe, just maybe, the key to moving forward isn't always about finding the perfect choice, but about choosing before it's too late. Imagine declaring that tomorrow will be opposite day, a day where everything means the opposite of what is said. If someone tells you it's raining, it actually means the sun is shining. If they say, I'm happy, they must be sad. But here's the paradox. If tomorrow is truly opposite day, then when you say, tomorrow is opposite day, does that statement itself get reversed? If the declaration is true, then tomorrow must be a normal day, contradicting the original claim. This is the opposite day paradox, a mind-bending linguistic and logical puzzle that demonstrates how self-referential statements can lead to contradictions, much like the liar paradox, where a statement like, "This sentence is false," collapses under its own weight. Opposite day presents an issue where language and meaning become unstable the moment they attempt to define themselves. At its core, the paradox arises from self-reference and negation. If language has an agreed-upon meaning, and opposite day forces every statement to mean its opposite, then any attempt to state that opposite day exists contradicts itself. The phrase, "tomorrow is opposite day," inherently erases itself because on that day, statements must mean the reverse of their intended meaning. This leads to a logical loop in which the meaning of the statement cannot stabilize. The paradox might seem like a playful thought experiment, but it has deeper implications in logic, philosophy, and even artificial intelligence. How does meaning remain stable when the very rules governing meaning are in flux? Consider a more practical version of opposite day. If a society collectively agreed that all laws meant the opposite of their wording for one day, how would governance function? Would no parking signs mean parking is allowed? Would crimes be rewarded instead of punished? The instability caused by such a reversal would lead to chaos, showing that meaning relies on consistency. This paradox also raises questions about communication and human perception. Words only have meaning because of shared understanding. If that agreement is suddenly upended, language itself falls apart. Children often playfully invoke opposite day as a way to tease one another. But as soon as one person declares it, the others can challenge the idea using the same logic. If today is opposite day, then you must be lying about it. The infinite regress of contradictions highlights the fragility of meaning when forced into paradoxical conditions. Even in artificial intelligence and computer programming, opposite day presents a fascinating challenge. AI models rely on logical structures to interpret language. But if every input were forced to mean its opposite, a system would require a stable baseline to interpret meaning accurately. This suggests that for communication, whether between humans or machines, to function, there must always be a foundation of fixed truth. Otherwise, interpretation collapses into an endless loop of reversals. Opposite day is also relevant in philosophy and epistemology, the study of knowledge. If everything we say or believe could suddenly mean the opposite, how can we ever be sure that our understanding of reality is accurate? It forces us to consider whether truth is absolute or context-dependent. This idea extends into real-world scenarios. Political doublespeak, propaganda, and misinformation often operate by subtly distorting meaning, creating an effect eerily similar to an imposed opposite day. So how do we resolve the paradox? The simplest answer is that opposite day cannot logically exist in a formalized sense. The moment you declare it, you undermine its validity. The paradox demonstrates a broader principle. For a system of meaning to function, it must contain unshakable anchors of truth. Without them, the entire structure collapses into incoherence. In the end, opposite day is more than a fun childhood game. It's a linguistic and philosophical experiment that forces us to grapple with the very nature of meaning. It reminds us that while language can be playful and flexible, it ultimately relies on shared understanding. And perhaps the true lesson of opposite day is that meaning itself isn't just in the words we use, but in our agreement to understand them the same way, something that paradoxically, opposite day refuses to allow. Imagine a world where every action you take has already been determined, where your choices are illusions, and your fate is sealed before you even make a decision. This is the heart of the free will paradox, a thought experiment that challenges our deepest intuitions about autonomy and determinism. At its core, the paradox arises from the clash between determinism and free will. Determinism is the idea that every event, including human actions, is the inevitable consequence of prior events and natural laws. If this is true, then every decision you make was already set in motion long before you were born. On the other hand, free will suggests that humans have genuine agency, that we are the authors of our choices and could have acted differently under identical circumstances, but can both be true at the same time. One of the most famous illustrations of this paradox comes from Laplace's demon, a hypothetical intelligence that, given complete knowledge of the universe's current state and the laws of physics, could predict the future with absolute certainty. If such a being could exist, then free will is an illusion. We are merely playing out a script written by the fundamental forces of nature. Yet our subjective experience tells us otherwise. When we choose between coffee or tea, or decide to take a different route home, we feel as though we are actively making choices. But is this just a trick of the mind? Neuroscientific studies suggest that our brains may initiate decisions before we are consciously aware of them, implying that what we perceive as free will is actually a post hoc rationalization of predetermined neural processes. But the paradox deepens. Suppose we embrace determinism and accept that all choices are preordained. What does that mean for morality and responsibility? If a criminal had no real choice in committing a crime, can they truly be held accountable? Some philosophers argue that compatibilism offers a middle ground, the idea that free will and determinism are not mutually exclusive. According to this view, even if our choices are influenced by prior causes, we can still be held responsible as long as our actions align with our internal desires and reasoning. On the other side, hard determinists reject this notion, claiming that true moral responsibility is impossible in a deterministic universe. If everything is causally linked to the past, then punishing someone for a crime is no different than blaming a rock for rolling down a hill. This paradox extends beyond philosophy and into physics and quantum mechanics. Classical physics operates under deterministic principles, but quantum mechanics introduces probability and randomness at the fundamental level of reality. Some argue that quantum indeterminacy leaves room for free will, but does randomness truly equate to freedom? If our actions were dictated by chance rather than deterministic laws, that still wouldn't grant us meaningful control over our choices. The free will paradox also seeps into theology and metaphysics. Many religious traditions grapple with the tension between divine omniscience and human agency. If an all-knowing deity already foresees the future, do humans truly have the power to make different choices? Some argue that divine foreknowledge doesn't necessarily imply predestination, while others see an unavoidable conflict between omniscience and free will. So is there a resolution? Some suggest that free will is an emergent property, not an illusion, but a complex phenomenon that arises from deterministic processes. Others believe that we must simply redefine our understanding of choice, seeing it not as an unrestricted ability to do anything, but as a nuanced interplay between cause and effect. In the end, the free will paradox forces us to confront the limits of human understanding. Are we the masters of our fate, or merely passengers on a predetermined path? Perhaps the true answer lies not in solving the paradox, but in recognizing that even questioning it is an exercise of our own supposed free will. Imagine a race between the mighty warrior Achilles and a humble tortoise. Achilles, being much faster, allows the tortoise a small head start. But as Achilles begins to chase, a strange thing happens. Every time he reaches the point where the tortoise was, the tortoise has moved a little farther ahead. No matter how fast Achilles runs, he can never quite catch up. This is Zeno's Achilles and the Tortoise Paradox, one of the most famous paradoxes in the history of philosophy and mathematics. At first glance, the paradox seems absurd. Of course, Achilles will overtake the tortoise. Yet Zeno's reasoning appears flawless. The core of the paradox lies in the division of space and time into infinitely smaller segments. Achilles must reach the tortoise's starting position first, then the next position, then the next, and so on. Since there are infinitely many points he must pass, how can he ever finish the task? If an infinite number of steps is required, shouldn't Achilles be trapped in an endless chase? Zeno's paradox challenges our understanding of motion and the very nature of infinity. It suggests that movement is impossible because it requires completing an infinite sequence of actions. This contradiction troubled mathematicians and philosophers for centuries, raising fundamental questions about the nature of space, time, and continuity. One possible resolution comes from calculus, developed centuries later by Newton and Leibniz. The concept of limits allows us to sum an infinite series of smaller and smaller distances to reach a finite result. In this framework, Achilles does indeed catch the tortoise, because although the number of steps is infinite, the total time required is finite. This mathematical breakthrough provides a logical resolution, yet the paradox still raises deeper questions about how we conceptualize infinity and motion. Beyond mathematics, the paradox has profound philosophical implications. It forces us to ask, is the world continuous, or is it made up of discrete steps? If space and time are infinitely divisible, does this mean we can never truly move from one point to another? Modern physics, particularly quantum mechanics, complicates the matter further by suggesting that on the smallest scales, space and time may not be continuous at all. The paradox also serves as a metaphor for real-world struggles. How often do we set goals, only to find new obstacles appearing just as we make progress? It mirrors the way progress in life, technology, and science often feels like an infinite chase, where each solution brings new challenges. Ultimately, the Achilles and the Tortoise Paradox continues to captivate minds across disciplines, from philosophy to physics to computer science. It reminds us that even seemingly simple concepts, like motion and progress, can unravel into profound and unsettling mysteries. And so, like Achilles, we keep running, not just toward the finish line, but toward a deeper understanding of the infinite complexities of reality. Imagine a list of all interesting numbers, numbers that stand out due to some special property. Perhaps they are prime, perfect squares, or hold significance in mathematics or nature. Now imagine defining an interesting number as any number that has some unique property worth noting. But here's the paradox. If such a list exists, then there must also be a number that is the smallest uninteresting number. Yet the moment we identify this number, it suddenly becomes interesting by virtue of being the smallest uninteresting number. And so paradoxically, no number can truly be uninteresting. This is the interesting number paradox, a mind-bending paradox that arises from self-reference and the nature of classification. Much like the liar paradox, where a statement contradicts itself, or the Sorites paradox, where gradual change creates uncertainty in categorization, this paradox reveals how definitions can unravel under scrutiny. At its core, the paradox exploits a contradiction in our reasoning about properties. If interesting numbers are a well-defined category, then there must exist numbers that do not belong. But the mere act of defining an uninteresting number contradicts itself, because we have just made it interesting. The paradox plays on the ambiguity of language and classification. What exactly makes a number interesting? Some numbers, like 1, 2, and 3, are clearly significant for fundamental mathematical reasons. Others, like 1729, are famous due to historical anecdotes. Srinivasa Ramanujan identified it as the smallest number expressible as the sum of two cubes in two different ways. But what about 89 or 5023? They may not seem remarkable at first, but they likely have hidden properties that would make them interesting upon deeper examination. This paradox isn't just a clever word game. It has implications in mathematical logic and artificial intelligence. In programming and database structures, categorizing objects requires clear-cut rules. But if the boundary between categories shifts based on the act of labeling itself, how can we define absolute properties? This issue extends into machine learning and AI, where algorithms attempt to classify data, but can struggle when definitions rely on context or human interpretation. The paradox also touches on philosophy and human perception. What makes something interesting? Is it an objective quality, or is it entirely subjective? If interest is defined socially, by what mathematicians or scientists consider noteworthy, then our standards for what is interesting evolve over time. This suggests that categories we think of as fixed may be more fluid than they appear. Even in epistemology, the study of knowledge, this paradox raises deep questions. How do we classify concepts when defining a category can alter its meaning? It mirrors real-world issues in science and linguistics. where defining new terms can shift how we perceive and organize information. Consider the classification of species in biology, where drawing a boundary between one species and another can be surprisingly difficult due to gradual evolution. So is there a resolution? One approach is to accept that interestingness is inherently subjective and context-dependent. Another is to formalize definitions mathematically so that a number is only deemed interesting if it meets a specific criterion independent of subjective interpretation. But even this does not eliminate the paradox. It simply shifts it into a new form. In the end, the interesting number paradox is more than just a mathematical curiosity. It's a metaphor for the way we structure knowledge itself. It reveals that categories we assume to be concrete often dissolve under scrutiny, forcing us to rethink how we define, label, and understand the world. Perhaps the real lesson of this paradox is that nothing is truly uninteresting, because even the act of declaring something uninteresting makes it worth discussing. A closed box, a cat, and a vial of poison. With these simple elements, Erwin Schrödinger introduced one of the most mind-bending paradoxes in physics, Schrödinger's cat. It's a thought experiment designed to illustrate the bizarre implications of quantum mechanics, specifically the idea of superposition. Imagine a cat placed inside a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the Geiger counter detects radiation from the atom's decay, it shatters the vial, killing the cat. If no radiation is detected, the cat remains alive. The catch? According to quantum mechanics, until someone opens the box to observe, the atom exists in a superposition, both decayed and undecayed at the same time. And if the atom is in both states simultaneously, so is the cat, both alive and dead. A single observation forces the system to choose one outcome or the other. At first glance, this seems impossible. How can a cat be both alive and dead? Schrödinger himself wasn't proposing that real cats exist in such states. Rather, he wanted to highlight the counterintuitive nature of quantum physics. In the microscopic realm, particles exist in multiple states until measured, but applying this idea to larger, tangible objects like a cat creates a paradox that challenges our understanding of reality. This paradox raises profound questions about measurement and reality. Does observation truly determine the outcome? Is reality itself undefined until we interact with it? The famous Copenhagen interpretation suggests that the act of measurement collapses superposition into a single definite state. But alternative explanations exist, like the many worlds interpretation, which suggests that both realities persist. One universe where the cat lives, and another where it dies. In this view, every quantum event creates a branching of the universe, leading to an infinite multiverse of possibilities. Beyond physics, Schrödinger's cat has become a metaphor for uncertainty in many aspects of life. We often exist in states of indecision until an action forces a definitive outcome. Think of applying for a job. Until you receive an answer, you exist in a superposition of both hired and rejected. The paradox also relates to free will. Are choices truly ours, or are they the result of an underlying deterministic reality that only collapses when we commit to a path? Schrödinger's cat also intersects with modern technology. Quantum computing, for instance, relies on qubits, which, unlike classical bits, exist in a superposition of 0 and 1. This principle allows quantum computers to perform vast numbers of calculations simultaneously, unlocking computational power far beyond classical systems. The paradox, once a purely philosophical dilemma, now has real-world implications in the forefront of technological innovation. And then there's the question of consciousness. Some interpretations suggest that a conscious observer is required to collapse a quantum state. Does this mean reality only exists because we are here to perceive it? Could the entire universe be in a state of quantum uncertainty without a mind to observe it? The paradox forces us to confront an unsettling idea. Reality may not be as objective as we assume. Instead of existing in a single definite state, it could be a shifting landscape of probabilities, solidifying only when measured. If this is true, then what is real? And what role do we, as observers, play in shaping it? Schrödinger's cat remains one of the most fascinating paradoxes in science and philosophy. It challenges our notions of reality, observation, and existence itself, leaving us with a haunting question. If the universe itself is like the cat in the box, suspended in a state of possibility, then what happens when we finally open the lid? Imagine a world where a major crisis is averted, but no one notices. This is the essence of the prevention paradox, a counterintuitive concept that highlights how successful preventative measures can make problems seem non-existent, leading people to question their necessity. At its core, the prevention paradox states that an intervention that benefits the population as a whole may seem unnecessary to individuals because they never experience the crisis it prevents. This is especially relevant in public health. Consider vaccines. Widespread immunization prevents outbreaks, but as diseases disappear, skepticism grows. People start to wonder, was the vaccine ever needed? Ironically, the very success of prevention makes its necessity harder to justify. Another classic example is road safety. Traffic regulations, seatbelt laws, speed limits, DUI enforcement drastically reduce accidents. Yet because fewer people see the devastation of unchecked reckless driving, some may argue these laws are too restrictive. When prevention works, the problem fades from view, and skepticism replaces caution. The paradox extends beyond health and safety. Take economic policies. Governments implement regulations to prevent financial collapses, but when crises are avoided, critics claim the measures were excessive. Had the regulations not been in place, economic disaster might have struck. But because they worked, the threat seems imaginary in hindsight. It also manifests in climate action. Policies aimed at reducing carbon emissions prevent environmental disasters. Yet when they succeed, skeptics argue that the crisis was exaggerated. People only react to disasters they experience, making it difficult to maintain support for long-term preventative efforts. But the prevention paradox poses a dilemma. How do you convince people to invest in solutions for problems they don't see? This is a key challenge in fields like medicine, policymaking, and risk management. Should leaders allow small-scale crises to occur so people understand the risks firsthand? Or should they continue preventative measures, knowing that success might lead to complacency and backlash? Philosophically, this paradox raises questions about perception and human psychology. We judge reality based on visible consequences, but what about the disasters that never happened because of prevention? How do we recognize success when it leaves no evidence of what was avoided? It also touches on free will. If we preemptively solve problems, are we truly preventing disaster, or just altering the timeline to one where the crisis never existed? This links to the grandfather paradox. Does preventing an event mean it never had a chance to happen in the first place? The prevention paradox reminds us that the absence of a problem is not proof it never existed. It's often proof that someone, somewhere, took action before it was too late. It forces us to reconsider our assumptions about risk, responsibility, and the unseen forces shaping our lives. And perhaps it leaves us with a deeper question. How many disasters have been erased from history simply because prevention worked so well that no one noticed? Imagine writing a book filled with well-researched, carefully argued chapters. In the preface, you humbly acknowledge that, despite your best efforts, there may be some errors somewhere in the text. But if you believe each individual chapter is accurate, how can you also believe that some part of the book is likely wrong? This is the heart of the Preface Paradox, a philosophical dilemma that challenges how we think about belief, knowledge, and rationality. At first glance, it seems reasonable to believe each statement you make in a book. If you didn't think a chapter was true, you wouldn't have included it. But at the same time, it's also rational to accept that, given the complexity of the material and the possibility of human error, there's a high chance that at least one statement is mistaken. The paradox lies in this contradiction. How can you rationally believe both that all the claims are true and that at least one claim is false? This conflict illustrates a key tension in epistemology, the study of knowledge and belief. The Preface Paradox shows that holding individually rational beliefs can lead to a collectively irrational position. If every chapter is believed to be true, then logically, the whole book should be considered error-free. Yet acknowledging the likelihood of error based on statistical or historical precedent is also a rational stance. The paradox becomes even more pressing when we scale it beyond books. Consider scientific research. Each study is conducted with care, peer review, and rigorous standards. Scientists believe their results are accurate. Yet as a community, scientists also recognize that some studies will be flawed, whether due to experimental error, statistical anomalies, or unrecognized biases. This collective humility is crucial to scientific progress, but it also mirrors the exact structure of the Preface Paradox. A similar situation occurs in our daily lives. We make dozens of assumptions and decisions based on what we believe to be true, about people, plans, predictions, but we also recognize that not everything we believe can be right. So are we being inconsistent, or is this a necessary feature of rational thought? Philosophers have offered several responses. Some suggest embracing a form of probabilistic belief, where instead of treating beliefs as absolute, we assign confidence levels to them. In this view, we might be 95% confident in each individual chapter, but still accept that, across the whole book, there's a high chance at least one error has slipped through. Others argue for a revision of our logical principles, suggesting that it may be acceptable to hold inconsistent beliefs if they each have independent justification. The paradox also raises questions about the nature of consistency and coherence. Should a perfectly rational agent avoid contradictions at all costs? Or is some level of contradiction an unavoidable byproduct of navigating a complex, uncertain world? Some argue that consistency is an idealized model, not a practical requirement for real human reasoning. In politics, journalism, and law, the Preface Paradox plays out subtly but persistently. We expect policymakers to stand firmly by their decisions, yet also to admit when mistakes are made. We expect journalists to report facts with confidence, while acknowledging the possibility of retraction. The balance between conviction and fallibility is delicate, and when handled poorly, it undermines credibility. But when acknowledged honestly, it can foster trust. Philosophically, the Preface Paradox forces us to grapple with the limitations of certainty. It reveals that rational belief isn't always about achieving perfect consistency, but about managing risk, acknowledging fallibility, and striving for truth in an imperfect world. It teaches us that intellectual humility and confidence are not opposites. They are two sides of the same coin. In the end, the Preface Paradox reminds us that knowledge is not a static possession, but a dynamic process. Our beliefs, like the chapters of a book, may each be reasonable and well supported, yet still vulnerable to error. And perhaps the most rational stance is not to avoid paradox, but to embrace it as a sign that we are still learning, still questioning, and still growing in our understanding of the world. Imagine walking into a bar and someone tells you this: there is someone in this bar such that if they are drinking, then everyone in the bar is drinking. At first, the statement sounds absurd. How can the drinking habits of one person determine the behavior of everyone else? This is the heart of the drinker paradox, a logical riddle that challenges how we understand implication and reasoning. The paradox stems from a principle in classical logic known as material implication. In logic, a statement of the form, if A, then B, is considered true in all cases, except when A is true and B is false. That means if A is false, the whole statement is automatically true, regardless of B. This leads to counterintuitive outcomes. Let's break it down. Suppose no one in the bar is drinking. Then the statement is true, because the if part is false. Now suppose at least one person is drinking. We can choose that person as our subject, and if everyone else is also drinking, the statement holds. In either scenario, the logic checks out. This paradox reveals how formal logic can diverge from common sense. Most interpret, if someone drinks, then everyone drinks, as a causal or social claim. But in logic, it's purely structural. Truth-functional logic doesn't always align with intuition. Some philosophers argue paradoxes like this highlight a need for relevance logic, where implications must have meaningful connections. Others suggest the paradox isn't a flaw in logic, but a reminder that logic applied without context can lead to strange conclusions. The paradox has implications in fields like artificial intelligence and law, where systems based purely on logic may produce results that are valid but bizarre from a human perspective. Understanding it helps develop reasoning models that better reflect how people think. What makes the drinker paradox especially striking is how it illustrates the gap between technical validity and perceived meaning. It challenges our expectations by showing that statements can be logically sound, even when they seem completely disconnected from reality. In doing so, it forces us to question the assumptions we carry into conversations, debates, and analysis. It also reminds us that paradoxes aren't just intellectual puzzles. They're doorways into deeper understanding. By engaging with them, we learn to navigate the fine line between precision and absurdity, and we sharpen our ability to reason in a world that doesn't always follow neat, logical rules. Ultimately, the drinker paradox isn't really about drinking. It's about how structure can mask absurdity. It challenges us to ask whether truth lies in the form of statements or in the meaning we attach to them. And in doing so, it reminds us to examine not just our conclusions, but the reasoning that leads us there.